Hello everyone, welcome back to another video. And in this video, we're going to be taking a look at a question from the IB Chemistry Paper 1 HL from the May 2018 batch. And this is from time zone 1. So this question deals with periodic trends. And I think that chapter comes in topic 2 and topic 3. So it's kind of in between those two. Now, this is a very, very simple topic, right? It's all about understanding what they're trying to get, the concepts. And hopefully I'm going to be able to tackle some of the concepts here, mainly related to atomic radius and first ionization energy. Now, if we look at the periodic table, I'm just going to see, of course, I don't know what all the elements in the periodic table are, but I am just going to imagine that this is a periodic table. Okay, so over here we have the group one metals. And then over here, we have all the halogens. So we have like neon and so on. So here we have, sorry, not the halogens. I mean the noble gases. Here we have the noble gases. And then over here, we have the halogens. And you know, this middle section over here is the transition metals. Oh my God, my handwriting is so bad. I'm sorry. Here we have the transition metals and so on and so forth, right? Now you get a rough idea of what I'm talking about. So this is the group 1 metals like sodium, and then you have the halogens like chlorine, and then you have the noble gases uh, like argon, for example. So this is basically the trend. Now, obviously, this is just a very rough sketch, probably not correct, but you get an idea of what I'm talking about. So the general trend for atomic radius is basically, it's literally what it sounds like. If you imagine a singular atom of a particular substance to be spherical. So if it's like a circle, right? You have the nucleus in the center, and then you have these electron shells around it, right? You have the electron circling. And the atomic radius is quite literally the distance between the nucleus and the outermost shell. This is the atomic radius, right? It's basic math. It's just imagine a circle, midpoint to the end. That's the radius, that gives you the radius. Now the general trend for atomic radius as we move from the group 1 metals towards the noble gases and the halogens, the general trend is that atomic radius decreases as we move from left to right. Now, why does that happen? That happens because of two reasons. The first reason is that the atomic number increases. So if you check out your periodic table, the atomic number of chlorine is much higher than the atomic number of Na. That means that chlorine has more protons in its nucleus, right? And that would also mean that the attraction or the strength of attraction from the nucleus on the electrons is much higher, because remember, the protons, they keep pulling the electrons towards them because positive and negative charges attract each other. So they pull them in towards each other, and the higher the atomic number goes, that means the more protons there are, and the more number of protons there are, the stronger the effective nuclear charge, which is basically the charge or the force felt by each electron of the proton. So you can think of the nucleus like a magnet, and the electrons around it like magnetic substances. So it's literally pulling these electrons towards itself. And the second reason is that as you move from left to right, for example, in period 2, so if you move from left to right in period 2, the number of shells of each element remain the same, right? Because each element in a period, remember, periods are horizontal rows and groups are vertical rows. So when you move across a period, which is my way of saying when you move across a specific period, which is period 2, you see that the number of shells of the atoms remain the same because each element in the period has the corresponding number of shells as their period number. So an element in period 2 would have 2 shells, an element in period 3 would have 3 shells, right? So when you move across, you see that one, as I mentioned before, the nuclear charge or the atomic number increases, but the number of shells remains the same. And what does this imply? Well, this basically implies that the electrons that are circling around in these shells over here, right? Imagine we have all these electrons, they're just circling around in the shells, yeah? These inner electrons over here, to an extent, they can shield the outer electrons from the full attraction of the nucleus because they kind of intercept the attraction. If you think about it, they kind of intercept it, right? This is the nucleus, it's sending out its attraction forces, and these four electrons can sort of intercept that. But as you move from left to right, the number of shells remains exactly the same, but the protons, this nucleus keeps getting bigger and stronger, and the shielding effect of these inner electrons begins to reduce. They begin to, they kind of get overwhelmed by the attraction. And then consequently, you see these outer electrons over here experiencing a higher effective nuclear charge. You begin to see them feeling the stronger attraction of the nucleus as you move from left to right because of this shielding effect. So basically, the shielding effect is when the inner electrons shield the outer electrons from the full influence of the nucleus. But as you move from left to right in the same period, you begin to see that the electron shielding effect starts to decrease because the nucleus just gets bigger and stronger. And that's why the outer electrons are now actually under the stronger influence, or they're feeling the stronger influence of the nucleus, pulling it in together. And much like a magnet, it tugs it in towards itself. And that's why atomic radius actually decreases as you move from left to right because of the strong nuclear charge, which is pulling everything in towards itself, and the decrease in electron shielding effect. So with this new information, what can we eliminate from these options? Let's see. So A deals with atomic radius decreases down a group. We'll get to that later. First, ionization energy, we'll get to that later. C, atomic radius increases across period 3 from Na to chlorine. No, that's wrong, right? As we mentioned, atomic radius actually decreases across periods from the metals, the group 1 metals, to the halogens. That's the general trend. And for the two main reasons that I mentioned to you, increase in nuclear charge, I'm going to write it down over here, 1, increase in sorry increase in nuclear charge, and C, or atomic number, whatever you prefer to remember, because remember, atomic number is just the number of protons that are there in the nucleus. And the second reason is the decrease in electron shielding effect, ESC, SA, the decrease in electron shielding effect, and that I also mentioned to you earlier. So we can eliminate C. C is not going to be the right option over here. Now, let's take a look at the second thing. Atomic radius decreases down group 17. Now, the general trend for atomic radius down a group, remember, periods are horizontal rows and groups are vertical rows. So as you move down a group, so supposing you move down the halogen group, so it starts with fluorine, then it goes on to chlorine, then it goes on to boron, I believe, then it goes on to iodine, and so on and so forth, right? So as you move down these groups, you're not only moving down the group, but you're also moving down periods, right? Because supposing fluorine is in period 2, right? Sorry, right? Fluorine is in period 2. Sodium is in period 3. Bromine is in period 4. So as you're moving down the group, you're also moving down periods. These elements are in different periods. And you know that an element has the corresponding number of shells as their period number. So as you move down the group, you start with fluorine, which has 2 shells, for example, right? It has 2 shells, fluorine. And then you reach chlorine, which has 3 shells. And then you reach bromine, which has 4 shells. 1, 2, 3, 4, and it just keeps getting bigger and bigger. So as you see, that atomic radius is actually increasing, not decreasing. You can see from this example, it's increasing, and it's getting larger and larger because of the increasing number of shells. So we can eliminate option A. This is not correct either, because it actually increases down the group, not decreases. Now we're left with two options, B and D, and both of these deal with something called ionization energy. Now, what is ionization energy? Ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. And in very simple terms, this basically means how much energy is required to remove 1 electron from 1 atom. Now, we know something. We know that group 1 metals, they like to lose their electrons because when they bond or when they interact with other elements, they like to lose their electrons. So Na becomes Na plus, you know, Li becomes Li plus, and so on and so forth. And they like to lose their electrons because it is simply much easier for them to attain a full shell or to attain stability by losing an electron. Because remember, they have only 1 electron in their outer shell, right? So if they want to attain stability, or if they want to gain a full valence shell, they have two options. They can either gain electrons or they can lose electrons, because if they lose 1 electron, that entire shell disappears because they only have 1 shell in the outer shell, right? And then they are left with the next shell, and the next shell is full. So let me tell you what I mean. Let me draw that over here. Imagine you have lithium, right? Let's say you have lithium. Lithium has an atomic number of 3, if I'm not wrong. Let me just double check that because I don't entirely remember the periodic table. But if you flip over in your data booklet, because remember, you get your periodic table, just a manual copy of the periodic table in paper 1. So yeah, lithium has an atomic number of 3. That means it has 3 electrons. So it has 2 electrons in the first shell. Remember, the first shell can only hold a maximum of 2 electrons. And then it has 1 electron in its second shell. Now, lithium has two options to gain a full valence shell. It can either lose this electron, it can give it away, and then the shell would disappear and it would be Li plus, and there we go, it has a full shell. Because remember, the first shell can only hold 2 electrons. Or it has a second option. It can either keep this electron and then gain 7 more electrons. So it can either gain 7 more electrons, or it can lose 1 electron. Now, if you were lithium, which do you think is easier to do? Is it easier to lose 1 electron, or is it more easier to gain 7 electrons? Well, obviously, it is much easier to lose 1 electron. And by easy, I mean energetically. In terms of the energy required to do this, it is simply much easier to lose 1 electron than to gain 7 electrons. So that's why group 1 metals tend to give away electrons rather than receive them. Now let's take a look at halogens, the other spectrum. Halogens, I'm going to take the example of fluorine. So fluorine has an atomic number of 9, which means that it has 9 electrons as well. 2 in the inner shell. Remember, the 2 can only hold a maximum. The inner shell can only hold a maximum of 2 electrons, and 7 electrons in the outer shell. Now, fluorine also has two options. If it wants to become stable, it can either gain 1 electron, because if it gains 1 electron, it will have 8 in the outer shell, and that it means full shell. That means stability. Or it can lose 7 electrons. Now, if you were fluorine, what do you think is easier to do? Is it easier to just gain 1 electron or to lose 7 electrons? Well, obviously, it is much easier to just gain 1 electron rather than lose 7 electrons. So, fluorine would much rather opt to gain electrons than to lose. And that's why you see halogens forming ions like Fi minus, F minus, or Cl minus, or Br minus, right? Whereas you see Group 1 metals form ions like Na plus or Li plus or K plus. Now, for ionization energy, as I mentioned before, ionization energy measures the energy required to remove one electron from the atom. Now, as you know, group 1 metals, they can lose one electron very easily. It's energetically feasible for them to do so. And the reason for this is one, of course, as I told you, to gain stability, it is much easier for them to lose one electron. And second, they have a very low atomic number. So Na, for example, sodium has an atomic number of only 11. That means the nucleus isn't as strong as an other element compared to sodium in its own period. For example, let's take a look at chlorine. Chlorine has an atomic number of 17, and that means that its nucleus has a much stronger influence over the electrons. And if you want to remove one electron from chlorine, you have to supply enough energy to overcome the force or the attractive forces of the nucleus, and that requires a lot of energy. So rather than removing one electron, it makes much more sense to give one electron. Whereas for sodium, that's not the case. It can easily lose one electron. The, um, the nucleus doesn't have that strong of an attraction over the other electrons, so you're good. Now let's take a look at our options. First, ionization energy decreases down group 1. Now, as you move down group 1, as I mentioned to you earlier, it's the same in all elements. As you move down a group, the general trend is that atomic radius tends to increase, as you can see from this diagram. Now, if I replace fluorine with lithium and sodium, or sorry, chlorine with Na, it's the exact same thing, right? The atomic radius is the same. It has 3 shells. And then after Na, you have potassium, which has 4 shells. Now you see that the atomic radius increases as you move down a group. And that means that the valence electrons, the electrons that are in the final shell, are moving further and further away from the nucleus. This means that the nucleus, the grasp or the force of attraction of the nucleus on the outer electron decreases because they're getting farther and farther and farther away from the nucleus. And if you have ever played with magnets before, you know that if you get two opposing magnets like North Pole and South Pole close together or close enough together, they will automatically attach. But if you keep them at a distance, they won't do anything because remember, distance matters. The force of attraction gets weaker as you take an electron further and further away from the nucleus. So that's why ionization energy actually decreases down group 1 because it's more easier to overcome the nuclear force or the nuclear influence on the electron when it's further away from the nucleus, if that makes sense. So B is actually our correct answer. And let's take a look at D. First, ionization energy decreases across period 3 from Na to Cl. And I've explained that to you before, why that's not true. Because it is more energetically feasible for halogens like fluorine, chlorine, bromine, iodine to gain one electron than to lose 7 electrons. Therefore, ionization energy, which deals with the removal of electrons, actually increases when you move from left to right because halogens don't want to give up their electrons. They have a big nucleus, a strong nucleus. The nucleus holds a good attraction on the electrons, whereas for group 1 metals like sodium, that's not the same case. And it is easier, or the ionization energy is lower for sodium than it is for chlorine. Therefore, ionization energy increases across a period rather than decrease. And that's the general trend. So this is also the wrong answer. And B is our correct answer. I know this has been a confusing video. I've introduced so many new topics and concepts, but I hope you've understood what I've done. You have any questions regarding this or any other concept, please feel free to message me on my social media. I'll be more than happy to help you. Put it down in the comments below or send me an email. Thank you so much for watching. I will see you in another video with another question. Take care.